Welcome. I will show you how to do finite difference with Excel. Typically, we don't do this with Excel. Like for example, like Matflow will you will have an equation like this. It will be discretized numerically as something like this. But Matflow will solve an equation like this, not with Excel but with Fortran. Is a PFAS example, for example, that I showed you. They solve with a finite difference equation, which would look something along these lines. They solve it with MATLAB, for example. Yeah. But the reason I want to show you how to do this with Excel, because I want to show you the solution step by step, like how, because here you have the head, you are estimating head in space and in time. So space, this is like I is equal to 1, I is equal to 2, I is equal to 3, I is equal to 4, I is equal to 5. So head, like here head is already known as a boundary. So that's like your boundary condition. So your boundary condition here is giving like 8.2. So head here, like H1 is 8.2. And head here, like your second boundary condition, H5 is equal to 3.6. Now my question to you, what is like H2, H3, and H4? And how they change in space, but also how they change at different time steps. Yeah. So at each of these guys, we have like an equation. So this equation will give you this guy. This equation here will give you this guy. This equation here will give you this guy at the new time step, and how it changes in space. And for a system like this, like let's read our problem here. So let me delete all this, make it looks clean, and let's read our problem. So our problem, we are giving delta y is equal to 3 meter. We are giving delta x is equal to 1 meter, and we are giving delta t discretization in time, and that is equal 0.007 day. For example, we are giving delta t like the discretization in time. And K and B, K is as a hydraulic conductivity, B is the aquifer thickness, so K times B is as equal transmissivity. Again, this is not a groundwater class, so these details are not important. And these, like the important thing, what I want you to see here is that like how you have a partial or differential equation, how you will get this numerical formulation, and then how you solve it numerically, like step by step, iteratively, each step at a time. Yeah. So the transmissivity K times B, that will give you the transmissivity. Specific storage times B, that will give you the storage coefficient. And then here, this is the important part. So the important part here at time 0, like before the start of the simulation, my head was equal. So head here was equal to head here, was equal to head here, was equal to head here, was equal to 10.8. So let me draw this for you. So this is head, which is changing with y and time, function of space and time, and this is like y here. So let's assume, for example, this would be, so this is like I, like 1, for example, 2, 3, 4, 5, at different nodes here. So here, initially, the head here was constant. Yeah. So the head here was constant, 1, 2, 3, 4, 5. So that was like 8.2, 8.2, so on. But when my simulation start, here was 8.2, like the head here, but the head here dropped in like number 5 here to like 3.6. So this is at T0. So at T1, what will happen? So at T1, what will happen is that you will not find a sudden drop, but this guy will drop a little bit to here. This guy will drop a little bit to here. This guy will drop a little bit to here, and this guy will drop a little bit to here. So you will see something like this. This is at T1. At T2, what will happen? This guy will not drop because this is my boundary conditions. This will be something like this, something like this, something like this. So that is at T2. And at T3, maybe you get something that looks like this. Yeah, that is at T3. 3. Okay. So now we want to see how, so you see here how the system is evolving in space and how it is evolving in time. So I want to show you like how to do this numerically, basically. I have here for different boundary condition and different finite difference method, but again, these details are also not important. I just like want to show you the main idea. Okay. Uh, so here, let's look at this guy here. So this is my coordinate 1.5, 4.5, and you know why this is, because remember like we have like the central difference. Let me show you, like if you remember like the not the central difference, mesh centered and block centered. Do you remember something like this? So the mesh centered and block centered. So basically we estimate the head in the middle of each cell. So here, if the cell here, this is 0 and this is 3, and we estimate the head here at like 1.5. Here would be like 4.5 and so on. Yeah. So basically, I'm just showing where we are estimating the head at 1.5, 4.5, and so on and so forth. The delta y is giving, the delta t is giving in day, the storage coefficient is giving, the transmissivity is giving. Alpha, remember what alpha is? So alpha basically, we can take all these terms because this is constant, and we just can call this alpha, and we can take all this term and we can call this beta. Yeah. So alpha is giving, let me show you like what alpha is. Let me bring this for copy, paste. Yeah, so you remember. So that's what alpha is. Yeah. So if you checked here alpha, that would be 2 plus s plus and so on. Like you have like this equation for alpha, and like you have this equation here for beta. Yeah, so it's like s times delta y squared divided by transmissivity divided by delta time, and so on. This is my initial condition, like we start like at 8.2. My boundary condition in the left is 8.2 and at the right is 3.6. And now here I want to estimate the head at H2, H3, H4. So how to do this? Basically, here is the equation that you have. So H2, that would be equal to what? That would be equal to this value, yeah, plus this value, yeah, plus this value is unknown. So we take this value as the previous time step divided by alpha. So this is from this equation here, yeah, which is, so this equation here is basically like the general form of like these equations. So you're solving for h. So you bring h to the right hand side and you bring everything else to the left hand side, and then you divide by alpha, and then you get this equation. So basically like this guy would be equal to like this guy plus this guy times beta plus this guy divided by alpha, then you will have this value here. And then this value would be equal to what? It would be equal to this value plus this value plus this value time beta divided by alpha, and so on. And then you get like these values. For the Qn, or like the volume in, like Qn, like volume over like my delta t, like delta time, you basically use this equation. So that would be like your transmissivity. So like if you look here, that would be like your if you look here, that would be your transmissivity, this guy minus this guy divided by delta y times delta x, which is equal to 1 times delta t, and that will give you the Qn that's entering this cell. Q out would be, instead of like using these two guys, it will be like these two guys here. So like you see Q out, like I'm using these two guys. So that would be for this cell. For the next cell, what's Qn? It will be like the difference between this head and this head. Yeah, and what is Q out? That would be the difference between like this head and like what's going out of it, and so on. And the difference between Q in and Q out, that would be the change in storage basically, which you can uh, also calculated from the change in storage. Like we have an equation for the change in storage, so we can use the equation of the change in storage and compare it with like the Q in and the Q out, like how we did it manually, and you see they coincide. And basically, when this coincide, this means that you don't have much numerical error. Yeah. So this is basically how you do it for one time step. You can also, this is the mass balance. You can see here, this is Qn for this cell. And so that's be the Qn here for this cell. Uh, and and for this is like you can calculate like the storage for this cell. You can calculate the storage for this cell. And you can calculate the storage for this cell. And then you can calculate like the Q out for this cell. Like, so this is what's entering my model. This is a change in storage, a change in storage, a change in storage. This is what is leaving my model. And then here I can, what's coming in and what's going out, that would be equal to the change in storage. So like if I subtracted this guy from this guy, that would be equal to what? That would be equal to the change in storage. Okay. So that's basically the conservation of mass. But typically, like, so this is just for one time step, but I can repeat this for different time steps. So this is for my second time step, my third time step, my fourth time step, and so on and so forth. Here, like, I use the value from my previous, like at the initial condition. Here, I will not use the value from my initial condition. Like, so that would be, here, let me bring this equation here. So like for example, let's say this guy. This guy would be equal to what? This guy would be equal to this guy plus this guy plus the value of this guy from like my previous time step. So this guy here, like this guy here, like which is this guy is equal to what? It's equal to h minus I minus 1, which is this guy, plus I plus 1, which is this guy, plus like the value of this guy, but at the previous time step here. Yeah. So it will be like at the previous time step time beta divided by alpha. Then I got this guy. So you see here exactly what I have. So I have like this guy multiplied by beta plus this guy here plus this guy here divided by alpha. And then you do this. And now here I'm plotting not all the time step. I'm plotting a time step one. So before a time step one, so here this is, you see like how the head here is dropping gradually. Then at time step two, you see some slight drop in the head. At time step five, you see the head is dropping more. But then at time step like towards the end, you get like this linear relationship, which what we expect like this. The analytical solution for this equation at steady state is just a straight line, which we got, which is what we got here. And you see, like as you reach like to this steady state, you see the head is not really changing much in space. See, the head is almost constant in space, and you got this steady state solution. So basically, that is how you can solve this problem with Excel, and that is basically how head will change in space and in time. So what is the learning objective here? So the learning objective here is that I want you to see how these models work in the background, and whether this model is a groundwater model, a surface water model, contaminant transport model, heat transport model, all are the same. They all have the same element. What are these elements? They all have a differential equation. This differential equation, you discretize it in this way, and then after you discretize it in this way, you solve it using a numerical method, like iteratively or through other methods that we will learn later. Yeah. such as like linear algebra or things like that. Yeah. And again, like this would be also like involve like iterations. Like all these methods will like involve these types of iterations. So now, if you don't understand much of this, that's fine. That's like kind of an advanced topic, or not advanced, but like you learn how these models work, and so that's very useful because, for example, when you read the manual of any of the models that you are using, you will learn, okay, like we are using this finite difference method or finite element method, and this is our numerical equation would look something like this, and then we will solve it using this method or that method. Yeah. So that's all for this. Again, this video is optional. You don't need to watch it. Uh, I just want to give you an idea about these topics just so that you have knowledge, be knowledgeable about not just using a model, uh, but knowing what is like how this model works and like the basic ideas behind these models that you are using. Again, the emphasis, that's the main emphasis, by the way, of this class. Yeah. If you want to know, like, for example, how to use flow or how to use another model for flood modeling or whatever, this is in a specific class. So groundwater hydrology class, I don't cover this topic, but I mainly show you, okay, this is flow. Flow is solving this equation, which you would like know like the meaning of this term, but now how to input like this term, how to create a grid, how to input this term, how to run the model, and how to process the results from this model. That's basically. But here you learn more of these basic concepts. Okay. Again, if you don't understand much of this, that's fine. Don't worry. But uh, you can, yeah, you can tell me in the exit ticket, for example, how much you understood. Okay. Okay. Thank you, and see you in another video.